let's prove the strong Casanova lemma of green. So what does strong Casanova lemma say? That if we have at least n plus 3 points in linear general position in Pn, then this is different from 0 if and only if x is contained in a rational normal curve. So first of all, if x contained in a rational normal curve C, then beta n minus 1 n of C is lower than or equal to beta n minus 1 n of x, and this is different from 0 for the minimal resolution of a rational normal curve. So that implies that this is different from 0. Hence, this group is different from 0. Conversely, if kn minus 1 of x is different from 0, we want to find a rational normal curve which contains x. So, as you might guess, this would be a syzygy variety. So we will reduce to the theorem we have just proved. So how to do that? We choose y in x, a subset of n plus 3 points. Well, if x has exactly n plus 3 points, there's nothing to prove, because any n plus 3 points in linear general position lie on a rational normal curve. The real statement is that when x contains more points than n plus 3, then we know that there exists a unique C, a rational normal curve, such that y is contained in C. Now I claim that the restriction kn minus 1 C to kn minus 1 y, this is an isomorphism. Let me take this for granted for the moment and see how this can be used. So assume the claim. How do we proceed? Well, if we have the inclusion, so we will also have so an inclusion of y in x will give an inclusion of the Koszul homology of x in Koszul homology of y. So we have k minus 1 of 1 x is included in kn minus 1 of y, and this is isomorphic by the inverse of the restriction to kn minus 1 kn minus 1 of C. And now if we take alpha different from 0, which is a syzygy of x, then this will be a syzygy of y, which will be a syzygy of C. So alpha is in kn minus 1 of C. And we have proved that the syzygy variety associated to alpha is actually C. But now, if we take a Koszul class, the syzygy variety contains the original variety. So, but x is contained in the syzygy variety of alpha. And we get our inclusion. Now let's prove the claim. So proof of the claim. So what do we get? Well, what do we have here? We have n plus 3 points on a rational normal curve. So we have n plus 3 points on P1, and P1 is embedded by O of n. So for any Q, we have any positive q, we have a short exact sequence. Actually, we can write it directly. So we have a short exact sequence So here we have the homogeneous coordinate ring of C, which is direct sum of H0 of P1, O P1. So P1 is embedded by O of n. So we take the multiples of n over Q. Here we have the restriction over Y. And the kernel is the direct sum of H naught of P1, OP1, Qn, minus how many points? Minus n minus 3 points over Q. So these three are all graded modules over S. So we obtain a long exact sequence for Kozulko homology, which is the following. So we are interested in Kn minus 1, 1 of C, Kn minus 1, 1 of Y. Here we will have Kn minus 1, 1 of P1, O of minus n minus 3, O of n. And it goes to Kn minus 2 to P1, O of n minus 3, minus n minus 3, sorry, O of n. P1, P1. So we are fine if we prove that these things vanish. So we want Kn minus 1, 1 of P1, O minus n minus 3, O of n. So this plays the, I mean, this gives the embedding, this plays the role of that coherent sheaf F. P1, P1, and this to be 0, and Kn minus 2 to P1 of minus n minus 3 of n equals 0, P1, P1. So we want to prove the vanishing of these ones. And for that, we will use kernel bundles. So remember how they were defined. We had V, which was the whole space, OP1. This goes to O of n, which gives the embedding. And let's call the kernel M. So these were computed from global sections of, so there was a co-kernel from something to H0, or a kernel from H1 to something. So if we are going to use the H1 description, so I can erase this. So, for example, Kn minus, before doing that, what is this M? So the degree, the rank of M is n. The degree of M is minus n, and M has no sections. So what can this be? So that implies that M is a direct sum of minus 1 n times. So we know what this M is. Now kn minus 1. 1 of p1 of minus n minus 3 of n was isomorphic to the kernel of a map from H1 wedge n m tensor this guy of minus n minus 3 to something. And k n minus 2 of the same thing was isomorphic to the kernel H1 wedge n minus 1 m tensor of minus n minus 3 plus n. So that would be minus 3 to something. So we will actually prove that these H1s vanish. And this is now rather straightforward, because wedge n of m would be O of minus why is it no, sorry, no, I don't want to do that. I cannot prove the vanishing of H1 directly. I have to apply, so let me see. No, I have, sorry. This is correct what I've written, but I cannot prove the vanishing of H1. So let me apply duality first. If we apply duality, then kn minus 1 1 of p1 of minus n minus 3 O of n is isomorphic. The dual of this one actually is isomorphic to k01 of p1 and O p1 of n plus 1 O of n, which is k02 of p1 O of 1 O of n. And this one is now the kernel of some H1 of, here we have 0, so that would be m tensor of 1 to something. And now m is a direct sum of minus 1, so this is 0. K02, did I, just a second, H1, K02, we have to tensor, sorry, so it's n plus 1. But that's 0 nevertheless, because it's a direct sum, it's a number of copies of H1 of O of n. And now, similarly, Kn minus 2 of the same thing, dual, is isomorphic to K11 of P1 of 1 of n, P1, and this is the kernel of a map from H1. And now, since we have K11, here we will have wedge 2 of m tensor of 1 to something. But now wedge 2 of m will be a number of copies of O of minus 2. So here we have a number of copies of O of minus 1, and it has no H1. So this is again 0. Right? So the claim is proved. Hence the strong Casanova lemma is proved. So as you see, the strong Casanova lemma relied on so that rational normal curve which appears in the strong Casanova lemma is actually a syzygy variety. So it is obtained, it is an instance of geometry obtained from syzygies. And now let me give the definition of a syzygy scheme in general. If definition, if X in Pn is a variety, non-degenerate, and P is at least 2, and suppose we have Kp1 different from 0, then define the syzygy scheme sits P of X to be the intersection of all the syzygy schemes associated to classes different from 0 in Kp1 of X. So that's somehow a variety which contains it's a scheme which contains our original variety X. And one goal would be to understand and possibly classify these schemes. So what are they? So the tendency is that those syzygy schemes tend to have small degree. So I said tendency because there are two, so we try to classify these syzygy schemes, and there are 3 cases when they are classified. 2 are obtained by Green. We have the following theorem, which is known as the Kp1 theorem, and is due to Green, 84, which states the following. If X in Pn is a smooth projective variety of dimension m, linearly normal, then first thing is that Kp1 of X is 0 for any P strictly bigger than n minus m. Second is that n minus m 1x is different from 0 if and only if X is a variety of minimal degree. So that's actually obtained from that theorem, that the syzygy variety of a rational normal curve is the rational normal curve itself. So we have to prove that that's a variety of minimal degree. We just have to consider hyperplane sections until we get to a curve, and prove there that the statement holds true. And each time we take a hyperplane section, it will drop the dimension of the ambient space. So we get exactly to that theorem, that the syzygy scheme of a non-zero extremal syzygy of a rational normal curve is the rational normal curve itself. And then another result, which would be the next case, if the next one is different from 0, then either x is an m-fold of minimal degree, case which is also caught by the other one, or is of degree 1 bigger than a minimal degree, which is n plus 2 minus m, so very close to minimal degree, or x lies on an n plus 1 fold of minimal degree. And this n plus 1 fold of minimal degree is a syzygy, scheme. Actually, if we want only to use the syzygy scheme language, we should say that if this is different from 0, then the syzygy scheme SIDS n minus m of x is either x and is of degree n plus 1 minus m or n plus 2 minus m, or it is an n plus 1 fold of minimal degree. So that would be the restatement in language of syzygy schemes. So I'm not going to prove the second part. It's just that I have to mention that it's much more involved and it uses strong Casanova lemma. So 2 follows basically after many steps from the strong Casanova lemma. Or there is an alternative approach, which I'm going to discuss a bit later. But before doing that, let me give a corollary, which I will collect these corollaries here. So the corollary says the following. We have x, a curve of genus at least G, at least 3, I guess. If I got it wrong, I will correct it. And L, a line bundle of degree D on X with D at least 2G plus 2. So H0 of, put H0 of L is N. N, of course, is D minus G from Ring-and-Roch. And assume that K n minus 2, 1 of X is different from 0. Then X is hyperelliptic. And for this, we apply Green's. So let me give a proof. I will just keep the statements here of the corollaries. There will be another corollary and I will keep the suspense for a while. So let me give a proof of that corollary. So we apply Green's KP1 theorem. Which says that either C is a rational normal curve we are in this case. So from Green's KP1, it implies that either X is a rational normal curve, which is not possible. Genus is at least 3. Or it is of degree n plus 1. But if it's of degree n plus 1, then it's of genus 1. Or of degree n plus 1, i.e. genus equals 1. And again, it's a contradiction with the assumption that the genus was at least 3. So what's left is that it lies on a surface of minimal degree. Which is, as we know, it's either a Veronese in P5 or it's a scroll, a two-dimensional scroll. But it cannot be Veronese in P5 because if n equals 5, then the genus is must be, so d n is 5, d minus g is 5, and d is bigger than g plus 2. So that, let's see, d minus g, 5 is d minus g, is bigger than g plus 2. So g is lower than or equal to 3. So yes, it was wrong. Genus is at least 4 here. Okay. Then genus is at least 3, which is again a contradiction with, so I should correct here everywhere. Genus is at least 4. It's a contradiction. So S is not a Veronese surface. So we are only left with S is a two-dimensional scroll. So it has a ruling. And having a ruling, so this is S, and our curve is somewhere here. So my claim is that, so this is C, and this is S. My claim is that the fibers of the ruling intersect, sorry, this does not C, is X. Intersect S in 2 points. Not more than 2 points. If we have this, then they will give a G12. And we obtain the curve is hyperelliptic. Why? If they intersect in 3 points, then we get a 3-secant line. And if we get a 3-secant line, then the bundle L minus these 3 points is special, right? Because they impose less conditions on the linear system L. So this must be special. And if this is special, then it means that the degree of L minus 3 points, or let's put this degree minus 3, is lower than or equal to 2g minus 2. We don't have special bundles beyond this range. But then that would mean that the degree of L is lower than 2g plus 1, which is a contradiction. So in conclusion, these fibers all intersect the curve in 2 points, and they will cut a G12 on the curve. So you see, it's a very nice result actually, how to get geometry of the curve out of syzygies. So we get hyperellipticity is characterized by this property.
Okay, n-3 or n-2?
No, it's n minus 2.
No, so you take the n large n equals to h.
Sorry, that's n plus 1.
Yes,
yeah.
L minus.
Yeah, but it's yeah. That's embedded in Pn as usual. Yes. Yeah, of course. Thank you. Okay. Now, what's generalization of?
So
Yeah.
this theorem, it is assumed that the variety is linearly normal.
Yeah. That also, yes, linearly normal.
Linear normal and the positive dimension? No.
And positive dimension, yeah.
Yeah, positive dimension. Yes.
So what can you say without assuming linear normality?
Oh, I don't know because not being linearly normal means that it comes from projection. But you can also project minimal varieties of minimal degrees, and they don't have minimal degree anymore in the projective space. So you can still have scrolls, which are interesting from the geometric point of view, which are not of minimal degree if they are not embedded. So it becomes a mess. So if it's not linearly normal, I don't know.
So KPN number 2, you assume linearly normal, right? 0, 1 is already known.
0, 1, for 0, 1, maybe you don't need, it doesn't matter, yes.
Doesn't matter, it is
But just for safety, I put it here in the...
So where did you use the linear normality of given variety?
in 2.
In 2, yes. In the proof of 2. Yes.
Where
But also, I mean, I think also for 1, you know, I mean, once you speak of variety of minimal degree is linearly normal already. So it's also for 1 is needed. Only for 0 is not needed. But somehow it's implicit also in 1.
Number 1?
Yeah. Well, X is a variety of minimal degree, so it's automatically linearly normal.
Yes. That is non-zero. That is should be linearly normal.
Yeah. Yes. Yeah. So it somehow it includes this hypothesis of linear normality. So yeah, probably a better statement would be that for 1, if this is not linearly normal, then this is non-zero. It implies linearly normal, and moreover, it is a variety of minimal degree. Yes, because in the proof before we didn't use, or we did because it was a rational normal curve. Yeah. Well, anyway. So now the generalization. The next step, if we look at least for curves, that was for kn minus 2. What happens for kn minus 3? And that was a theorem due to Ebauer, a student of Frank Schreier. Now he's not in mathematics anymore, so he's a very rich guy working for a German company. It's a pity for mathematics, but probably it's better for him. I don't know. So if X is a smooth, irreducible curve of genus.
But my question, K-P1 theorem for green, they assume smooth.
Yeah, it's smooth. Yeah, should be smooth. I don't remember very well but this comes in the proof. You need smoothness of genus.
But 0, 1, you don't assume smooth.
For 0, 1, no, but again for 2 you need smoothness.
But 0, 1.
No, but again, it's implicit somehow. And, yeah. So what happens for a cone? If you take a cone, I don't know. I don't know. We have to think about it, yes. Okay, anyway, so Ebauer's theorem was for curves of genus G, and now the genus, I didn't write it in my notes, should be in his paper, if I have it. Yes, so genus 13, probably. Now it's of any genus. Okay. Genus G. L very ample. Of degree of L bigger than H0 of L plus 14. H0 of L is N plus 1. And suppose that k n minus 3, 1 of x is different from 0. Then the syzygy scheme n minus 3 of x is either can be surface of minimal degree, and the minimal degree is n minus 1, or a surface of degree 1 more than the minimal, degree n, or a threefold of minimal degree n minus 2. So the proof goes differently from the KP-Mont theorem. So his idea is to use projection of syzygies. So his idea was to project as much as possible to get to curves in P5 and to analyze curves in P5 and prove the statement actually for n equals 5. And there in P5 you are more down to earth. You have lists of varieties. And he analyzes all the equations. It's a very elaborate analysis, and he finds one of the three possibilities.
The projection, inner projection?
Inner projections, yes. It's about inner projections. Okay, and now let me write down the corollary to Ebauer's theorem, which is very close in spirit to this corollary. So if x is a curve non-hyperelliptic curve of genus G at least 13, and L in peak D of x with degree at least 2G plus 3, H0 of L is n plus 1, n is D minus G, and suppose that k n minus 3, 1 of x is different from 0, then x is trigonal. So the proof is very similar to the proof of this corollary. because we have a list of surface degree n or threefold of a minimal degree. So let's give a proof. So proof. Let's take SYZ n. Look at S to be, or we have x, y. Y SYZ n minus 3 of x. From his theorem, there are exactly three possibilities. So it's either a surface of minimal degree, but this cannot be possible because if it's a surface of minimal degree, then as before, it will give a G12 on x. So y cannot be a surface of minimal degree. So that's claim 1. So for the proof, act as before, exactly as before. Claim 2, y cannot be a surface of degree 1 more than the minimal degree, which is n. And why is that? Because surfaces of degree 1 more than the minimal degree have been classified by Nagata. So Nagata proves that if y is in Pn with n at least 10 is a surface of degree n, then it's either the image of a projection of an outer projection of a surface of minimal degree in Pn plus 1, or a cone over an elliptic curve. So this cannot be a projection because y is, x was was linearly normal, was considered to be linearly normal. So if it was contained in an outer projection, then that would prevent it from being linearly normal. So
Here, y is a smooth surface?
no, because no, the classification is for any, because the cone is not smooth.
But also you consider isometric projection or the image of arbitrary projection, minimal degree surface?
Yeah, if you have a minimal degree surface in Pn plus 1, and you take a point, so that's of degree n. You take a point which is not on a surface and you project, you get a surface of degree n in Pn. That's one of the cases. And the other case is the cone. So it cannot be a projection because the projection will not be linearly normal. And this will prevent also the curve to be linearly normal. So we have to analyze what happens to suppose y is a cone with vertex P over an elliptic curve E, right? And prove that this is not that's not possible. And the proof goes again by similar. So if we have, this is our E, the elliptic curve. Here's the vertex, that's P. And this is the cone. And our curve X is contained somewhere here. So that's X. Now let me, probably I don't write, I just draw the picture. Let me choose a point Q on the elliptic curve and draw this line. So it's quite clear that this line will hit X in at least 2 points. For otherwise, if a general line will hit X in 1 point, then it will the genus must be 1, which is not possible. So we have at least 2 points of intersection. Maybe there are more. Let's take now another line with Q prime. We have again 2 points of intersection. And what do we get here? So we have a plane which intersects the curve in at least 4 points. So that means that we get a 4-secant 2-plane. But then this implies again that L of minus 4 points is special. So H1 is different from 0. But then the degree of L minus 4 must be bounded by 2g minus 2, i.e. the degree is bounded by 2g plus 2, which is a contradiction with the assumption we made. So in conclusion, the only possibility is that X lies on a 3-dimensional scroll. And now if it's a 3-dimensional scroll, it has a ruling with planes. And these planes again will intersect the curve in 3 points. For if a plane would intersect the curve in 4 points, we get a 4-secant 2-plane. And again, L minus the 4 points will be special. So the ruling gives a G13 on X, and that's a proof. And now the question is where to go further. I would like very much to know the answer to this question. So probably the next case would be when Kn minus 4 is different from 0. Then this is we should be able to say something about the syzygy varieties, and they would produce a G14, because there is a conjecture made by Green and Lazarsfeld, which is called the gonality conjecture. Which states the following. So if we have X a smooth curve, L a line bundle on X of sufficiently large degree, so we would like to say that the degree is something very concrete. But if n minus k1 of X is different from 0, then there is a G1k on X. So ideally, the bound is, if we follow that pattern, ideally, the bound would be 2G plus K. Okay, and this is now, it was a conjecture until August. Now it's a theorem. It was published in Publication IHS by Ein and Lazarsfeld. So the gonality conjecture is valid with a bound 4G, of the order 4G.
D is bigger equal to 4G.
Yes, instead of 2G.
But in their paper, they remark that Lemma from 2G plus something.
No, they obtained 4G.
But
And they hope to get down to 3G.
but in the remark, right after Ramanan proved that D is very nice bound 2G times something. In that paper, when it is published in the journal. No.
So this paper is published in 2015. So that's 2015. So it's as new as this year.
Yeah. Well, as I remember, like their first bound was very bad, like G.
Yeah, it was G squared or G cubed, something like that. And then
they found a new nice.
Yeah, they found a new bound, but it's about the order 4G, if I remember well. It's linear in G, anyways.
What's their key idea to get the linear bounds on G?
Yeah.
Do you know what's the main idea?
I don't know right now, but we can look in the paper. So I read this paper, but it was some time ago, so I don't remember the. But anyway, their proof is completely different from. So they don't use syzygy varieties. They use other techniques like symmetric products of the curve. Yeah. So there is still some work to do on this gonality conjecture. I mean, can it be improved, this bound? I don't know. So if you take this approach with syzygy varieties, then you see that you can do much better than 4G. So it's always 2G. Because it's always the same principle of L minus some points being special or not when you have a list of syzygy varieties. So what I'm trying to say is that if you have a full classification of syzygy varieties, which is, I mean, it's out of reach for the moment, but there is some hope to go to the next step, for example, then you can do much better than the bound, because the method is very powerful. The other method is also powerful, but they are different methods. Okay, so I think I'll stop here.
Thank you. Thank you very much.
You're welcome.